continues our idea of the probability distribution. Probability distribution, we know, is like all of our outcomes and the probability of each. And we talked about one specific probability distribution in the last unit, the binomial distribution. Remember, that one was when we had a fixed number of trials. The outcomes were either yes or no. The probability was the same every time. They were all independent. However, all the ones we've talked about so far have been discrete. Like everything was countable. We haven't talked about any of our continuous variables with our probability distributions yet. So that's what's going to happen in this next unit. Today, we're going to talk about two specific things. A probability density function, sometimes called a PDF, is just an equation that can be used to calculate probabilities in a continuous situation. Still, we know total probability has to be 1. Every individual probability has to be greater than or equal to 0. We can't have negative probabilities, and they all have to add up to 1. So that is still true. The most simplistic probability distribution that deals with continuous variables is the uniform distribution. And that's a situation where every outcome is equally likely. So, for instance, suppose that United Parcel Service is supposed to deliver a package to your front door, and the arrival time is somewhere between 10 a.m. and 11 a.m. Let the random variable x represent the time from 10 a.m. when the delivery is supposed to take place. So it could be at 10 a.m., which is when x is 0, or 11 a.m. would be x equals 60. With all 1-minute intervals of times equally likely. So they are just as likely to come between 10 and 10:01 as they are to come between 10:35 and 10:36. Okay, every minute is equally likely. I want you to draw a graph of the distribution. So my y is my probability. My x here is my time. And this is starting at x equals 0. When would it end? 60. I am not going to put 60 tick marks. I'm just going to go 0 to 60 here. Okay. The probability is the same for every minute. So no matter which minute I'm at, my probability is the same. So it's just going to be a flat line across. All of these have equal probability. Could you tell me, though, what that probability is?
0, 1, 6, 6, 7.
How did you get that?
1 divided by 60.
Okay. I'm just going to keep it in fraction form just for the ease of labeling on our graph. Why would I do 1 over 60? There's every minute in an hour, there's 60 minutes in an hour. The total probability is 1. So you had to take our probability of 1 divided by the total length of time. Okay, so if it were a 15-minute time interval, what would our probability be? 1 out of 15. All right. Not very interesting. If it's uniform, everything has the same probability. It's just creating a rectangle every time. So using that, let's answer some questions. Find the probability of choosing a time between 15 and 30 minutes. Okay, think about what this means. If I wanted to put some more specific. If I said my time was between 15 and 30, then I'm talking about this little section. A probability density function is basically a graph where the area represents the probability. How do you find the area of a rectangle? Length times width. All right, so my length is what? 15. That's how far it is from 15 to 30. My height of that rectangle is? So 15 out of 60, or 1/4.25 if you prefer. Which makes sense. There's a 15-minute window. So 15 out of 60. All right. B, there is a 30% chance your package will arrive within the next blank minutes. Okay, think about how we did this. We did our minutes, which we don't know, times the probability. And if I want a 30% chance, that would have to be equal to 0.3, right? So if I multiply over my 60, what's 0.3 times 60?
18.
So it's a 30% chance we'll get our package in the next 30 minutes. Sorry, next 18 minutes. Okay, any questions about that uniform distribution?
Where did you get like X from?
I was just trying to find the number of minutes. So up here, I was just setting it up like this one where 15 was the number of minutes. And I was looking for that, so I just called it X. So, relative frequency histograms. So we've talked about histograms before, just like a bar graph. If I'm graphing the relative frequencies, if I get a shape that is symmetric and bell-shaped, okay, we've talked about those before, right? Skewed left, skewed right, and bell-shaped, and I told you bell-shaped was really important. That is what we call normal, right? Now, is this graph perfectly normal? No. What would happen if I added more rectangles?
Closer.
Right. The more you add, the smoother the curve would become, the closer to being perfect it would be. I mean, we've talked about that before, like the more trials we have, the closer it gets to our expected value. The normal curve has a lot of important properties, and we will be focusing on those a lot tomorrow. But in a normal distribution, if you look at that bell-shaped graph we've talked about, the peak of it is our mean. We know this is the mean plus and minus the standard deviation, right? And we could do 2 standard deviations, 3, and so forth. So what we need to know right now is, if it's bell-shaped and symmetric, that is the normal distribution. Our properties, it's symmetric about the mean, so that means the area on the left-hand side would be the same as the area on the right-hand side, or 50-50. 50% chance of being below, 50% chance of being above the mean. It's symmetric. Total area is 1, and our empirical rule works. Remember that empirical rule, it's on our formula sheet, we've talked about it a few times. 68% of our data is within 1 standard deviation, 95 within 2, 99.7 within 3. Alright, so is this graph normal?
Yes.
Yeah, it's bell-shaped. What would make it not normal?
It was skewed.
Skewed. Yep, so this one is normal. Okay, can you tell me what the mean and standard deviation are?
2.
The mean is 2. How did you get 3?
Just
2 plus 3.
5
Mhm.
plus 2.
1 standard deviation would have to give me these points. 2 plus 3 is 5, 2 minus 3 is -1, so our standard deviation is 3. Do you guys see how we got that? So take a second on this one. Before we say it out loud, I want everyone to try it. Both of these graphs have a mean of 10. Would you agree with that? 10 is the peak on both? One has a standard deviation of 3. The other has a standard deviation of 2. Decide which is which. So don't say it out loud, just think about it on your own first. What happens when standard deviation gets bigger? It spreads, right? Standard deviation is a measure of the spread. And all we've said before is the bigger standard deviation, the more spread out. So 3 is a bigger standard deviation. That means that curve should be more spread out. Which one is it? B, because it's a wider, fatter curve. So that means A has a standard deviation of 2. Is that okay? Tomorrow we'll start calculating areas under these curves, and there's 2 different interpretations. We can talk about it as a proportion of the population with a certain characteristic, or the probability that a random individual would have the characteristic. For instance, if I said 62% of the students in my first hour class are female. Okay. The ways I could describe that, I just did the first one, the proportion of the population with our characteristic. So 62% of my class is female. The second way would be saying, if I selected a student out of my first hour class, the probability they are female is 62%. So you could use it as a description of the whole, or the probability that one would have our characteristic. So using that, we're going to answer this question. The weights of giraffes are approximately normally distributed with a mean of 2,200 pounds and a standard deviation of 200 pounds. Draw a normal curve with the parameters labeled. I cheated and I put a curve on here because I have a really bad time drawing perfect curves. So you get to draw your own bell-shaped curve. This middle point represents what? The mean, 2,200. And then, within one standard deviation, so to the left and to the right, can you tell me what those points would be? Because you just added and subtracted your standard deviation to get those. All right, so there's our standard normal curve. We labeled our mean and we used our standard deviation to get some points. Part B, shade the area under the normal curve to the left of 2,100. So 2,100 would be here, area to the left. Part C. Suppose that the area under the normal curve to the left of 2,100 pounds is 0.3085. Provide 2 interpretations of the result. So what is one thing I could say about that? It can be interpreted as
The probability of a point being in the shaded area is 0.30.
good. So the probability. If I want to be more specific, we're talking about weights of giraffes. So a giraffe weighs would be greater than or less than? Less than 2,100 pounds is 0.3085. So there's 30.85% chance that a giraffe I pick has a weight under 2,100 pounds. What is the second way we could interpret it? That's what we did there. So the other thing would be to use it to describe the whole population. So the proportion of giraffes weighing less than 2,100 pounds is 0.3085. So that's like saying if I took all the zoos in the Midwest, then finding the probability that one giraffe weighs under 2,100 pounds is 0.3085. If I look at all the giraffes together, 30.85% of them weigh under my 2,100 pounds. So you can think of it as a probability of one or a proportion describing your whole population. Those are the 2 applications. All right, any questions there? So this section is fairly short. I am stopping here today though. Tomorrow, we are going to start section 2.